have any questions during the talk, feel free to jump in. I'm happy to answer any of them. So as the title reveals, today we're going to talk about optimal vintage factor analysis with deflation varimax. So it's a bit complicated title, but it can mainly compose two parts. One is statistical part that is related with the factor analysis. This is related with a very famous procedure that has been used for 60 years. So we try to understand what this procedure does for us. And the second one has the optimization element. It gives us a kind of procedure, which is called deflation procedure, tries to solve a non-convex optimization that tries to find a orthogonal matrix. Okay, so that's has two kind of flavors in this talk. Okay, great. And this is a joint work with my colleague, with my collaborator Xin from Shanghai University Finance and Econometrics, and Yu Qian from Rutgers. So she's in the ECE department at Rutgers, and Diane is her student by the time this work was conducted. So I'll start with a brief introduction on what is the vintage factor analysis, because this is going to be the theme of this talk. And this is going to also give us a procedure that has been used for more than 3 decades. So I'll start with the factor analysis. And this is a very, very popular type of analysis done in statistics. So essentially, what this type of analysis tries to do is try to infer some low-dimensional representation from a high-dimensional measured features. So here we have P features here that can be measured, which can potentially, the P can be very large. So you can measure many, many things in these days. And the factor analysis tries to infer some latent, unmeasured, summarized factors, what they call, from these P measured features. So this is the essential idea of factor analysis. So a classical application is in sociology, where design questionnaires ask subjects to, for instance, to give a score for their happiness, to give a score for their certain moods. These are something you can directly ask the subjects to answer. And however, what the researchers more interested in to find out is some kind of latent summarized information from the subject. For instance, the subject well-being. And this data you cannot directly measure. It can only be inferred from these answered questionnaires. So this is just one application of this factor analysis. They try to summarize those measurable things to form some kind of knowledge of those unmeasured latent factors that people are interested in. And as a factor analysis, mathematically, because I'm giving a talk in this mathematical and stats department, so I would like to put the math notation first. So mathematically, it's very simple. When we have n data points from those P features, we come up with a data matrix, and we're interested in to learn a low-dimensional representation of each of the data points. Okay, so that's the mathematical notation. And as I mentioned, it has wide applications in many fields. Okay, so what is the most common procedures for factor analysis? It comes up with the most well-known procedure called principal component analysis. And this is the widely used in factor analysis. And I would give some mathematical notation to make sure to bring up the target that we're interested in here. So for PCA, we are given a low dimension R. So that is typically much smaller than P. This is the number of latent factors we are trying to understand. And if we write this XX transpose matrix as P by P, we do an eigen decomposition, and the PCA corresponds to use its first R principal components by using its first R eigenvectors as well as its eigenvalues. Okay, so here this UR matrix, instead of by n by P, instead of being n by P, this is n by R. Okay, so now for each of these data points, you only have a R dimensional vector, which is in low dimensional space. That's kind of the low dimensional representation of the high dimensional feature. And because of the nature of PCA, the rows, the columns of this UR are orthogonal. Okay, and those are going to be called principal components throughout this talk. And what is vintage factor analysis? So for factor analysis, you can think the previous principal components are the low dimensional representation, are the factors that people are interested in. And what is the difference from the vintage factor analysis? So the vintage factor analysis proposed to further rotate those principal components after PCA. And for certain purpose, right? You need to define what is the purpose you want to rotate those pieces. And according to Thorson in 1935, he gave 5 simple rules to rotate those structures. So mathematically, it means we want to find an orthogonal matrix Q in the low dimension R by R. And then to multiply these principal components in order to obtain a rotated factors. Okay, hopefully this URQ, this whole matrix, would satisfy certain structure. Okay, he gave a way of defining what is the appropriate structure we are seeking for. Briefly speaking, it mainly seeks, after rotating, those whole matrices are kind of sparse so that you can get more interpretation there. I'll give more details later. And of course, this corresponds to one part of the rotation. If Q is an orthogonal matrix, then there are 2 kinds of classically used rotations. One is called varimax, and this is going to be the core of this talk. So it corresponds to one choice of this orthogonal matrix Q to rotate. And there is another one called quartimax, and also you might choose Q to be not only an orthogonal rotation, it can be any kind of non-singular transformation, and that all corresponds to that is called oblique rotation in factor analysis. There are 2 choices for that. Nevertheless, in this talk, we're going to focus on this varimax because despite of these choices, varimax has been the most widely used, and it was proposed in 1958. But since it proposed and it has been used for many years, there is a long-standing controversy of its use because many people think varimax, specifically rotation within the principal component space, doesn't make any statistical sense. But there are a bunch of people who are still trying to apply it and find some meaningful results. So there is a long-standing controversy of its use. The negative part is based on the first image here. So the main idea of the criticism comes from the following. So if your latent factors are standardized Gaussian, then we all know it's invariant to any kind of orthogonal rotation. So that means if you further rotate in this subspace, it makes no difference statistically. So that's the main criticism of why rotation cannot be applied, should not be applied. But people are still finding some meaningful results after rotating their P6. For instance, I'm just giving one example. In the middle figure, you see those data points are more or less aligned in 2 linear hyperplanes. Okay. And once you do a rotation, that essentially meaning you are trying to rotate to find a new basis for all those points to have new different coordinates in the basis. And after this rotation, most of the points are well aligned with the coordinates, with the axis. So that means their interests or their coordinates in those new bases tend to be sparse. And this is also what people found in practice, like doing a PCA and then doing a varimax rotation. Most of the rotated principal components contain very close to 0 interest.
So just a question clarifying. So this is not a distribution of the data, it's a distribution of the principal component.
Yes. So Archer's question asks whether this distribution is imposed on the data or imposed on the low dimensional structure. So this is the data points I plotted are the low dimensional representations, not the original data.
You just generated this low dimension.
Yes, this data points are just generated, simulated. These are from the real data practice, actually, a real data application. You print their principal component and they look like the following in 2D space. Yeah. So, and this type of phenomenon that after rotating, all the low dimensional coordinates tend to be sparse is termed as a radial streak, okay, by Thurston in 1947. And people have constantly finding this pattern by using principal component. And this is the positive part, because this being sparse means you have more interpretability in the rotated space. And the question is whether there is any statistical justification for this. And this has been a long-standing problem until the GRSSB discussion paper in 2022 by Carl Roth and Mo He Zheng from University of Wisconsin. And they answer the following question. So varimax, after the principal component, does make statistical inference, but under a certain model. Under which kind of model? The following model they consider is X the original data is approximately low rank. Okay, it can be factorized as a loading matrix A, as well as a low-dimensional representation Z. Moreover, this is not enough. It further assumes that entries of Z has to satisfy two key properties. One, all the entries must be independent. Two, the Z distribution of Z being here is a leptokurtic. Later, I'm going to give you the definition of leptokurtic. At this point, you just need to know, as long as Z is not Gaussian, this rotation makes sense. And this doesn't really contradict with what we gave before. Okay. So this is the first paper who answered the following question, that varimax does make statistical sense under this type of model. And specifically, they show that if you can estimate this, find this rotation matrix Q, and then if you further rotate the principal components, you obtain this latent factor Z. So that's more or less the idea of this paper. Before moving on, I'm going to give you a quick definition of what is a varimax rotation, because this is very important for us to point out the difficulty of understanding this procedure. This is a very complicated math equation. This defines an optimization problem where we try to find the orthogonal matrix Q in dimension R by R. And the main idea of the objective function is the following. So we are trying to find the rotation Q such that after this rotation, the resulting matrix, its squared entries has a very large variance. Okay, so it makes the squared entries of the rotated matrix has very large variance. That's essentially what it does. And it can be simplified to the following extent. So essentially, it looks at all the possible rotated matrix so that its entry-wise L4 norm is maximized. This is not proposed by us, but this is proposed by Kreiser in 1935 and has been used forever since then. Okay, so this is the mathematical equation that we're talking about for varimax. Okay, now we look back at the ongoing issue of this GRSSB discussion paper. Typically, basically they show that the global solution to this varimax, which is their Q hat, they computed from the varimax package, they assume that this Q hat can be solved. Once this Q hat can be solved, this Q hat, after using this to rotate the principal components, would give you the Z under their modeling assumption. However, at this stage, they only talk about this defined maximizer of this function, of this optimization problem. There are there are at least two questions here. So first, if you look at this optimization question, this is because of this constraint set, this is a Q is in the Stifel manifold, the set of all orthogonal matrices, okay? And this is a highly non-concave optimization problem. And it's very notoriously difficult to solve and to analyze. Okay. So this is the thing. There is a big gap between the estimators they try to analyze, Q hat, versus the actual one they can compute in practice. And the second one is, what if your data is not approximately low ranked? For instance, a well-known or commonly used factor model is the following. So you have an additive arrow E on top of those low rank components. What about when under this model, what would the varimax delivers? So that's the second question. And the third question, following up on this model. So this is a classical factor model, and a kind of very interesting aspect of this model is try to understand the loading matrix A, which is the P bar R matrix. So that essentially tells you how those components are related with each of these latent components. So the estimation and identification of this A is also a very important research question to study. So in this paper or in this research, what I'm going to try to do is try to answer each of these questions. So we give specifically we give a statistical and both statistical and computational guarantees for applying the varimax plus PCA procedure under this model. Okay, in order to do this, you first need to understand what are the principal components consist of. For this, we give a new decomposition of the principal components under this model. And then the second step is try to understand what does the varimax do by applying to those principal components? So we design a new deflation procedure of computing those orthogonal matrices. And that one, more importantly, has provable guarantees. This is the main difference from the existing literature. And the third one, we demonstrate this whole procedure can not only use to construct this low-dimensional representation, but also can be used to estimate this loading matrix under this model. And of course, and moreover, this procedure can be minimax optimal. And there is some interesting thing in between. In order to achieve optimality, you need to figure out some bias and try to modify the procedure, not directly using the existing procedures for this purpose. Okay, so I'm going to answer all of these questions in this talk. So before commenting more, I would like to talk a little bit about the existing literature on the last point, which is estimation of this loading matrix A under that factor model. Because this turns out to be a classical statistical model, and there are many classical results on this. So first, I want to point out that classical factor analysis are mainly interested in the column space of A, not this matrix A itself. Because for using PCA, you essentially cannot recover A, but only space, column space. And that is also one of the criticism of just using PCA to extract low-dimensional structure, because you have some ambiguity in that space. Although there exists some identifiability conditions under which this A can be identified, but according to Anderson and Rubin in their paper, none of these existing conditions are inherent meaningful. So, and on the other hand, if you propose to rotate those factors, existing literature only focus on how to compute those rotations, but they don't really give a theoretical understanding of what this rotation does for us. In my PhD work, we consider several structured estimation under that factor model for A, and we give identifiability and by assuming certain structure. But in this work, we're going to focus on a different set of conditions by using the one in Rowe and the Carl, that GRSSB paper. Yes.
Can you provide some motivation why, what kind of cases where we want to recover exactly A rather than the space?
Yes. He said a very good question. Like under factor model, under which case we want to exactly recover this A instead of only recovering the column space of A. Right? For instance, one example is if you think you have your measured X and if you want to infer the Z. Well, I can shift this emphasis to Z because in the model X equal to AZ plus E, you can insert any invertible matrix in between. So for instance, Q and Q inverse. Okay, so I can call this AQ as another new A, and Q inverse Z transpose another Z. Okay, so without identifying A means you cannot exactly see what are the factors are. Okay, so that's one of the, in many cases, researchers want to know exactly what are those latent factors they want to interpret, not only interpreting within certain space. Okay, yeah. Also, I'll give you later one real data application for this. That's a very good point. In this paper, we're just following on the assumptions imposed by Carl and Rowe by assuming that the interests of Z are independent and are non-Gaussian. The moment I said this, if you're familiar with the literature of independent component analysis, you immediately recognize, is there a connection with that model? Indeed, ICE is another classical statistical approach to extract independent sources from a given feature. However, our model includes their corresponds to the ICE model if there is no additive error and if there is no low-dimensional structure. Okay, later I'm going to see our analysis actually covers this ICE. And there are also other procedures proposed once you assume independence and non-Gaussian entity in the latent space. I just referring them here. Okay, so now I'm going to give, before talking about everything, I want to give you the main modeling assumptions we're considering in this paper to analyze this varimax plus PCA procedure. So we assume this linear factor model and the interest of the latent factors are zero mean, standardized, sub-Gaussian tail. Those are very standard assumptions, and the zero mean can be made without loss of generality. And more importantly, we assume independence and the leptokurtic, which I'm going to explain in the next slide. And the loading matrix A essentially needs to be full rank because we want to define this low dimension there. And the condition number is bounded. And for the additive arrow, I simply assume it's Gaussian. And there is one important quantity I want to point out, which is epsilon square. Okay, because the ZA, this product, we call this as a signal, and this E is some additive noise, and this epsilon square represents this inverse of this signal to noise ratio under this model for inferring this low dimensional structure. Okay, so this epsilon square will appear constantly later. All right, so this is everything about the modeling assumption. Before that, I want to give you some intuition of what is the specialty of being leptokurtic for Z. Okay, independence is something we can understand, but what about this leptokurtic? It essentially means the following. It's a excess kurtosis is greater than 0. And for Gaussian, this is 0. Okay, so this is one way to say it's not Gaussian, but not the only way. Okay, and what is other property of this? You might wonder under which conditions, distributions of Z, this leptokurtic assumption satisfies. So in their paper, they gave that if the Z, interest of Z, has non-zero mass probability at the 0 point, okay, that means this hold. So essentially means being leptokurtic means it could be that some of the interest can be exactly 0. And this links the sparsity with the leptokurticness. And also, they also prove this soft sparsity can also hold for leptokurtic. And there is some other classical examples. Okay, but I want to point out this is essentially saying that's non-Gaussian and corresponding to smaller than 0. There is another direction, and our procedure can also be modified to adapt to that case. I'm just using this case for illustration. Okay. All right. So under all the assumptions, we're now trying in the place to understand what this principal components followed by varimax does for us under this model. First, as I said, we need to understand what is the principal components under this model. And it has a very simple mathematical notation. You have a original matrix multiplied by its eigendecomposition by using the first R components. Our first proposition gives the following decomposition of this principal component matrix. It has the following structure. The main signal is the first term. This Z is the latent factor Z, multiplied by some unknown orthogonal matrix Q star. Okay, this Q star there exists some Q star. And plus some additive arrow E prime and some arrow coming from the perturbation from PCA. The main thing I want to emphasize for this perturbation matrix omega is that its scale is controlled by this operator norm, denoted by this omega n. So from now on, the omega n is we can essentially think this is the noise level under this model. Okay, and it consists of 3 parts. One is the inverse of the signal to noise ratio. The other is only related with the low dimensional thing. That's more or less we can expect because we want to infer some low dimensional structure from ensemble. And the other one is mixed with this signal to noise ratio versus the ambient dimension. Okay. And this turns out to be the correct signal to noise ratio in this setting. But more importantly, from this proposition, what I want to emphasize is the following. This principal components essentially is approximately equal to Z multiplied by an orthogonal matrix. So now this suggests if the varimax can estimate this Q star, then further multiply this UR by that Q star will give you the Z. So this is all this proposition 1 tells us that we should hope or we should expect varimax actually estimate this Q star if you apply it on this UR matrix. And we're gonna confirm this by analysis. All right, so now the second part is try to confirm that the varimax, by solving this, does estimate this Q star. And we come back to this very difficult optimization question, which is non-concave. There are many ways to propose that you can try to solve this directly, but what I'm gonna propose is a simply easier task to solve this. essentially we are trying to solve this Q matrix column by column. Okay, I would like to understand if I can solve one column first to start with, and then I can think about how to extend this to solve the whole matrix. So for one column, this corresponds to the following optimization, where we are maximizing over this unit sphere. Because of this unit sphere, it's still a non-concave problem, right? So it's not a convex set. And there are many existing approaches to analyze this. However, all those analyses, according to my knowledge, has the following theme. It is a local result, saying that if you have a good initialization and in a local neighborhood, you have a contraction by using, say, gradient descent all the way until to the ground truth. That's all the local result I mean. However, how to get to the local point is unknown. Okay, and also this is specifically algorithm-specific dependent analysis. But in this paper, we're going to consider a different analysis, which is more general than this. So we want to characterize the optimization landscape of this in the sense that we're interested in the characterization of all first-order stationary points. If we're able to characterize all the stationary points, then we can identify those good ones and try to move away from those bad ones.
Just a structural question. What you're trying to do is actually maximize the convex function.
Yes.
Over a convex.
Yes. This is the question to try to clarify the structure of this optimization. It's a maximization of a convex function over a non-convex set.
Yes.
This is a unit sphere. Yes.
Yeah.
Yeah. Okay.
I mean, aren't there like regularizers which kind of enforce like let's look at the original problem that you actually want to solve, like these variational gram functions or something like that. Don't they, if you add them as a regularizer, don't they promote orthogonality? And then you would have like a difference of convex function optimization problem. Maybe we can discuss this offline. But
for the original one?
Yeah. I mean, there's penalty.
Oh, you mean you are saying instead of working directly in this set, right? You are working in the R matrix and adding some penalty to encourage.
To encourage. Yeah, I mean it's a relaxation.
Yeah, there are different ways of solving this directly. Yeah. But I don't think there is any theoretical understanding on the stationary points from the corresponding algorithm. But if you know something, maybe we can talk later. Yeah, you can point out to that references. Yeah, this would be great to know. Okay, so essentially this is our next step. We want to understand all the stationary points for this non-concave problem. So if we let this Q bar to be any kind of critical or stationary point, okay, and remember this Q star is the matrix that we think correspond to the global optimizer. Okay, so this is the ground truth we want to estimate. And we're able to characterize all the bad critical points in this problem by solving that optimization. So specifically at the population level, so this is something you take and goes to infinity. And this is a complicated structure, but all I want to say is that the bad critical point means it has the same distance to more than two true columns. Okay, it has the same distance to 2 columns, 3 columns, 4 columns. It only close to 1 column only. So for instance, in the case R equal to 4, those correspond to the structure of the bad critical points. So it's equally close to the first and second column, or to the first 3 columns, or to all of them. Okay, so this is the only structure in this optimization problem of those, like what we call the bad stationary points. So beyond this, all other stationary points are kind of good stationary points that we're going to give later.
Is that a statistical insight, or did you just crank that out of the KKT conditions? Second order optimality conditions.
That's a good question. This is saying that for this one, how do we derive this kind of structure in a sense, right? This is the first order stationary point. That means we take the first order gradient equal to 0, and we try to characterize all the possible solutions. Well, it's not the second order.
Constraint problem.
Yes.
So it's not just the gradient.
Right. We use a remaining gradient to characterize this. Yeah. That's I haven't been there yet, but that's true. Yes. Okay. So being able to understand this is the structure of the bad stationary points, right? Now Why do I call this bad? Because all the others should be good. That's essentially what our first theorem told us, that if you have any critical point that is, say, more closer to the first column compared to all the others by some noise level, okay, then we know that this critical point is already pretty close to the first column in the following L2 norm sense. So that's why I called all the other critical points are good. And just to remind you here, this ground truth Q star is a unit norm, and this critical point, because we're working in that unit sphere, is also a unit norm. You have this following property. And actually, I want to emphasize, this is a generic result in the sense that it holds for all stationary points, regardless what kind of algorithm you try to use. Okay. It's independent of specific optimization that you try to use. And in practice, right, we would like to choose one optimization to solve it. So then we try to apply this algorithm, this theorem, to one specific algorithm, which is the one we try to propose. We use a classical gradient-based algorithm to solve this. So now I rewrite this as a minimization. I try to use projected Riemannian gradient descent because this is a constraint optimization and this is the classical algorithm to use. And here, this is a Riemannian gradient, and you project it on the structure space that you on the feasible set, and this gamma is the step size you can play around. And actually, if you consider a matrix version of this, this is actually the default implementation of varimax in R. And for this projected gradient descent, if we apply the previous algorithm, right, what would this kind of what we can conclude from this algorithm is the following. It turns out that in order to ensure you have a good stationary point, you only need to ensure you have a good initialization. So the task gets simplified. So rigorously speaking, this is what we proved for this grid. If we were to use this gradient descent to solve that problem. So recall that this is something we want to ensure for a stationary point Q bar, because that means this is a good one and it's close to Q1. And now we are able to prove as long as you started with the initial point Q0, that is close to Q1 star by the same kind of noise level, then this Q0 would lead to a critical point that satisfies the following. So now in order to ensure a good critical point, it suffices to choose a good initial point. And the task seems to be simpler, however, not completed yet. Okay, so that's the whole point of this theorem. And moreover, this doesn't tell us how many iterations this Q0 would converge to a stationary point. That's what we call algorithmic convergence speed. And now our analysis also able to characterize this, as well as the effect of the step size gamma. So this is what I want to illustrate in this following figure. Now this is Q1 star in the ground truth we hope our algorithm would converge. And this red circle is the region where we would like our initial point to be initialized within. Okay, so now once we are in this circle, the first round of convergence happens as follows. So this L represents iteration, okay, L from 0, 1 to all the way up. So we're getting closer and closer to Q1 star compared to the initial point. And the convergence rate is linearly fast. Okay, and it depends on this gamma, which is the step size, as well as this new star is the gap between the initialization of Q0 to Q1 star versus the other column. So intuitively speaking, the larger step size or the better you initialize, this contraction happens fast. It will move towards to the ground truth. This is the first phase. And once you are reached to the blue circle, and then after onwards, the initial gap wouldn't really matter. What only matters is the step size. Okay, so now it converges to this Q1 star in the following way. So the convergence depends on 1 minus gamma. The larger the step size you choose, the faster it converges. Okay, and all the way until you reach to the statistical arrow, which is this with the radius equal to this green circle. That's the statistical error. Regardless how many iterations you run, you cannot do better in this way. And this is actually turns out to be later. We're going to talk about optimality of this later. Okay. And if we put everything together, we know that all this convergence happens linearly. So that means it requires at most log n iterations to achieve this statistical error. So we not only have the statistical error guarantee, but also the algorithmic convergence speed for this. Now coming back to this one column result. So modulo the initialization, okay? So we kind of solve this optimization for solving one column. But I want to point out that if we want to use this to extend to multiple columns, there are more efforts to work. But there is a one key observation from this result. I put circles here to indicate that the initialization is close to the first column compared to the other, and it gets close. It gives you a critical points estimate the first column. But this one is chosen very arbitrarily. You can replace 1 by 2, 3, 4, all the way up to R. The same result holds. So what does this tell us? This tells us that in order to estimate all the columns pretty well, you just find different initial points that are close to each column one at a time. And that will give you some critical points that are close to each of those ground truths. So this gives us the new deflation procedure, which is the following. We use the same projected gradient descent, run it R times. Okay, so this is the same procedure, same iteration procedure, you run it R times. The only difference is that you choose R different initial points. And this will give you R critical points from each of this round. However, there is one thing, they are not orthogonal just by this construction. So we won't have orthogonal matrix. So we do a orthogonalization in the end. Okay. And this is the whole procedure we have. And there is only one thing is that how to choose this initialization. Yeah.
What I don't understand is, I mean, you compute these little q's from the column version, what you want to do, and then you say you can orthogonalize them in a way that the resulting matrix, and how do you know it has any meaning for the problem you actually want to solve?
Yes, that's a good point. So the question asks, if we do orthogonalization in the end, right? How do we know what it estimates in the end? So the thing is that if you concatenate all those R columns as a R matrix, and from our previous results, we know that those are close to our Q star up to some perturbation. And now this orthogonalization can be done by SVD. And from classical, say, Davis-Cohen theorem, this is some kind of perturbation for eigen decomposition. And you can prove your orthogonalized matrix estimates this Q star better. Yeah.
Is it suggesting here that for initialization, we can get a good initialization for each column, and then put them together to get a initialization overall? But if we have there are many columns, then the chance of getting a bad one, for example, could be possible.
Yeah, I think the question is as trying to ask, right, how to choose this kind of different initializations that are close to, that are good for estimating each of these columns, right? I'm going to discuss how to choose initialization later. This is not the end of the story. I want to complete this thing. So if we put everything together, this is all we have modulo the initialization. If we were able to find our initial columns, that each of them is close to one of the ground truths, one at a time. Okay, now then they will lead to the final estimator Q hat that is close to this Q star in the following Frobenius norm. Omega n is a signal to noise ratio, well, is a noise level for recovering one column. So for estimating R columns, we are only lose another square root R. And now the question really boils down to how to complete this theorem, right? How do we initialize? We discussed two initialization schemes in the paper. I don't think I have time to discuss both, but I'll focus on random initialization and then briefly mention the method moment. Okay, there are two ways to estimate them. Random initialization is easier to implement, but it requires a stronger condition on the sample size. Method moment is computationally more expensive, but it requires weaker sample complexity. That's the whole idea. But the surprising thing is both of them work in this case. So random initialization, very simple. First column, you uniformly sample from the unit sphere. That's it. And for the other columns, you would want to make sure that you only sample from the unit sphere modulo in the orthogonal space of the previously recovered columns. And this will ensure that you won't really further sample from the space you have already recovered. Okay. And with this in mind, we can prove that this is the condition we previously required. You have this gap between the initialization from one column to the other. However, we require that this gap needs to be greater than the noise level. And this gives a final restriction for initialization. You require the noise level is smaller than 1 over r to the alphath power. And this, in turn, gives us a restriction on the sample size we need to have. This is a random initialization. Once this is satisfied, random initialization probably works. For method moment, I don't have time to talk about this specifically, but the main idea is to use tensor, fourth order tensor, doing multiple slicing, matching the moments, and that can give us the following. We can have the provable required initialization condition satisfied as long as the noise level omega is smaller than 1 over r. Previously, this is r to the 5th or 13th power. So this is the moderate condition. And both of the procedure works actually. And another thing, a byproduct. So method moment, by the definition, it would also give us some potential estimator for Q star by itself. However, its rates is not optimal because you have a noise level multiplied by r to the 3 over 2. Previously, we have 1 over 2. Yep.
What's the idea about this improvement? It's like basically you have different concentration for different of the distributions.
Sorry, you want to ask?
Why? How does you using this kind of multiple slicing make the convergence rate fast?
Yeah. So the question asks in what sense or how this method moment initialization can relax this condition, right? The whole point lies in the following. It ensures a larger gap between your initial point to one column versus the other. So here it becomes strictly equal to 1. If you look at this random initialization, it can only ensure the gap which is delta over square root r. This is a much smaller gap. So we need this gap, regardless of the magnitude, we need this gap to be greater than this noise level. So
I'm asking the step before, why you have this?
Yeah, why do we have this gap, right? So if we want to have this gap, this is all we require for the initial condition. The gap has to be nu has to be greater than the noise level. This is everything we are able to prove this one. So regardless what kind of initialization scheme you choose, we need this condition to hold. And then these two initializations, one is simple to implement, but it requires stronger sample complexity, restrictive sample complexity to meet that requirement. And the other one is more sophisticated, and it also relaxes sample complexity there. And in practice, when the sample size is small, we did find this is better. But if the sample size is large, both of them give you the correct result as our result revealed. Yeah. Okay, so this is everything. I want to briefly mention the existing approach for solving this problem because apparently in our audience there are some people interested in this. We want to mention why not we do not compute, like try to solve this problem altogether. What is the advantage of the following of our deflation procedure compared to this? So for deflation, typically you can optimize each column separately in parallel, and that can be faster to solve this whole optimization problem if you do a projected gradient descent on the whole manifold. And it can also be more flexible because in many cases, you can stop once you are satisfied with the latent factors you have already extracted. You don't need to finish all the extracting R components to start with. Okay. And 2, there is a more natural way to formulate a deflation procedure where when you want to compute the subsequent columns, you want to enforce its orthogonality to the previously recovered one. Okay, so this basically by doing this, you don't need a final orthogonalization in the end. However, if you're doing this, the error for estimating the first column would get translated to all the subsequent columns. And empirically, people observe an exponentially increased errors for using this constraint optimization. I want to point out this procedure is actually used in many statistical problems like sparse PCA, sparse canonical correlation analysis, etc. It potentially suffers this problem. And third, the one we propose can be really done in parallel. Yes.
I have a really naive question.
No, go ahead.
So obviously, the original problem, the constraint is Q transpose Q is the identity.
Yes.
Now relax that to Q transpose Q is less than or equal to the identity in the Lewis-Knot ordering.
Yeah.
Does that get, if I solve that problem, does that, have solutions which are completely meaningless for the original problem?
Yeah.
Because it's, okay.
Yeah, the question asks, instead of solving this original problem, what we're trying to solve is a relaxed version of this, where we relax this orthogonality constraint Q transpose Q equal to identity by Q transpose Q smaller than identity.
Yes.
Well, that smaller is a matrix smaller, right? And would the final result can the final estimator say, or stationary point can be estimated, can be analyzed? That's a good point. I don't know. Because this way we haven't I haven't tried to analyze this whole matrix for at this point yet. For solving this exactly, it's very hard to analyze, but a very natural way, if we consider to analyze this directly, is this convex relaxation as you suggested. But I'm not sure.
That is actually that because it's a convex set, it's a so-called difference of convex optimization problem, of which there's nice algorithms.
Yeah, but then you need to try to link the stationary point to the exact one, or you try to sort of get back to the optimal solution for the exact one. Right?
Yeah,
I think that's the main difficulty in the analysis.
Still a non-convex problem.
Right, exactly. But that's sounds more structured. Well, sounds more doable.
It has a lot of structure.
Yeah. But our next step actually is try to sort of understand solving this matrix version of orthogonalization altogether. Okay. I just want to briefly mention, although we are focusing on this structure, but our analysis is actually in a more general model. Specifically, it includes ICA, all those existing mentioned one as a particular model. So we're just using this PCA varimax as a running example. I don't think I have time to talk about loading matrix because I really want to present two numerical results related with this project. For the estimating the loading, I'll first give you a quick sense of what we have. We have minimax lower bound for estimating A hat in this problem. So this try to understand the difficulty of estimating A on our model. And this really is not a new result this is a new result in the sense that the latent distribution has to be leptokurtic non-Gaussian. So if you're familiar with the existing literature on minimax lower bound for estimating low dimensional subspace, everything is analyzed under Z being Gaussian. For Z being non-Gaussian, you need to construct different hypotheses to prove this minimax lower bound. So it doesn't follow from the existing literature. Okay. And the second one, I want to briefly mention how do we estimate A. This is very simple. I write two facts. The first line follows from PCA, the principle, the eigen decomposition, SVD, or the second one follows from our model. Okay, we have just proved the principal components are more or less Z transpose Q star. And that means the red part should match. And once you know Q star, this immediately gives us a way to estimate A by transforming back. So this is a very natural follows from varimax plus PCA. And then for this procedure, we can show that the upper bound is the following. It has original two terms plus one extra term. I want to talk about the following. It depends whether this estimator is minimax optimal or not, depends on the signal topology regime. If this one, epsilon square is small enough so that this term gets dominated by the first two, we get this rates, and this matches the minimax lower bound, hence the optimality in this regime. However, on the weak signal scenario, if epsilon square is not that small enough, you have some extra term here. And this, unfortunately, is not optimal. Okay. But fortunately, in this case, we are able to identify where the suboptimality comes from. I'll mainly give you two kind of sentences to describe the bias. One is to use principal component to estimate the low dimensional space. So that's the intrinsic bias from PCA for estimating Z. And the second one is once you have this principal components estimating this low dimensional space, if we are using projected gradient descent to solve the varimax problem, if you are having this additive arrow, that can give you another bias. And for both of the bias, if we know the covariance matrix of the additive arrow can be removed. And that will give us an improved estimator, which we call the noise version, that will achieve this minimax lower bounding on signal-to-noise ratio scenarios. So I also give you the way we estimate this Q matrix in this rate. All right, so this is everything about the theory. And now I want to present you two numerical studies related with in this project. So first, we would like to find some meaningful basis of the handwritten digits data. So handwritten digit data is the following. Each data point is just one number, and the input is some pixels of these images. You divide it into different pixels. And the goal is try to understand how these images are generated. So in this case, we have 8,000 handwritten digits, and each digit is represented as this 784 vector containing their pixels. Okay. And we are trying to understand from this data set, what is the low dimensional representation for each digit, and how these digits are related with those low dimensional components. So that essentially requires us to know Z to know A, and A times Z would give you this X. And that's what I'm explaining here. We want to learn this low dimensional basis. This is P by R. Once you know the basis, you can also plot this basis. And if you concatenate this basis by some linear combination, then you get your original X. Okay, so the coefficients Z are telling us which of these spaces contribute to each of the digits. Okay. All right, we compare our result, deflation varimax plus PCA versus just using PCA. These are the bases we have. We choose R equal to 49. We are considering 49 bases, and each one of them we can plot them here. And if you look at this basis constructed from two approaches, apparently the one from using varimax by rotating the principal components give you more information there. It's more interpretable. Okay. And the second part is if we're plotting the coefficients of the Z's, that essentially means for each digit, which kind of bases are connected with, are used to generate this digit. We selected 10 pairs out of this 49, 10 pairs out of the 49 pieces. And this is the for PCA, those are the coefficients. You can see that it's just like a spherical structure for X and Y coordinates. However, if you further rotate it, you'll find that most of the points are aligned with the axis. That means the coordinates are sparse. And that will give you a better intuition which kind of basis contributes to the digit. This is the first application showing that rotation after principal component does make a big deal in terms of interpreting the results and get a better low dimensional representation. The second one, which we try to understand, is if we have a mixed signal, okay, if we have a mixed image, I want to recover some signal from this image, can we use this varimax plus PCA? And this is a semi-synthetic data where we have 2 signal images and 3 Gaussian noise images. Okay, each one we treat it as a 171 plus 171 vector. And then for those 5 signal images, for those 5 original low dimensional images, 2 of them are signal, 3 of them are noise. And then we try to consider their linear combination in 100 dimension and then add some additive arrow here. So here in this case, these are the 5 original images we consider. 2 are signal, 3 are noise. And the second rule is that after mixing everything here, as this model suggested, these are the 5 examples of this X. You can see that it's hard. You can see something here, but it's hard to see what are the original signals from the final data accessible to us. Okay, so the goal here is these are the input. We try to recover those 2 signal images. And one is in the Seagull in New Jersey, and this is in Manhattan. I was doing this project while I was in New Jersey, so that's kind of the 2 images I picked up that matched my interest at that time. Okay, so how do we predict Z? As we said, we do a principal components, and we do varimax to select the rotation, and then we rotate. This is the Z hat. And we choose R equal to 5 because we know the low dimensional structure is in 5 dimensions. Although 2 are signal, 3 are noise. Okay. And we consider different procedures depending on the choice of Q hat. So for PCA d-varimax, this is the proposed procedure. And d-varimax 2, this is the bias corrected procedure that I mentioned before. Okay. And for PCA, it means you do not rotate. And also consider varimax, which is a classical implemented algorithm in R that compute varimax actually. So it's interesting to compare with the actual algorithm computed from this default package. I'd also consider some independent component analysis procedure here. So this is what we have to recover the signals. Based on the resolution, I think it's okay. Let me briefly walk you through. So the first 2 rows are the proposed algorithm. It recovers both signals pretty well. And the second row, if you cannot see clearly, improves on the first one in terms of resolution. This is the denoised version, okay, debiased version. And for PCA, sorry, this is the ICA, independent component analysis. It completely misses this Manhattan picture. And what's more interesting is the following. If you are considering the PCA, you can still maintain those 2 signals. However, it fails to separate those 2 signals away from each other. And that's exactly the point of rotating. And more interesting is the varimax as a default implementation in R. So we took their estimator and we tried to rotate. It gives a very unsatisfactory result. And meaning that it might just end up with some very suboptimal local solutions there. Okay. All right, so hopefully through these 2 real data, I demonstrated the point of using varimax PCA and also a specifically designed varimax procedure to compute or to solve that orthogonal matrix. And there are some methodological contribution by solving this non-convex optimization over the orthogonal matrix, the set of orthogonal matrix, as well as the procedure for estimating the loading matrix under factor model with this debiased procedure. And also the new method of moment estimation, although we just use it for initialization, it's itself like an independent result. It's itself a result of independent interest. And we have some theory supports our results. There are some future extensions. For instance, if you are consider the network analysis or the original or directly analyzing this matrix optimization, those are the future directions that we talk about. And also the final point, this is something interesting, but not rigorously formulated yet. We want to test the inference of the varimax in the sense that can we test whether a rotation after PCA is really needed statistically as a hypothesis testing problem. So this would correspond to test whether those Q matrix is equal to identity or just a sign permutation instead of being orthogonal. All right, so I think this is everything I want to talk about today. Thank you for your attention. I'm happy to answer any questions.
You must have a question or 2.
We have a mixed question with presentation, so yeah.
Well, just to start with, how dependent the results are. You assume that the noise matrix is Gaussian, right?
Yes, the
So
noise matrix
naive
is
question,
Gaussian.
How dependent are your results to that? And if you were to assume something else, like
Yeah. The question,
I guess it's just details, or is it more for the?
yeah, that's a good point. So the question asked for x equal to az plus e, right?
Yeah.
I assume e being Gaussian, is this really necessary or needed in the analysis? I move into this slide to say this is only needed for only one part in the de-bias procedure. So everything before this bullet 2, you can easily extend this Gaussian to any kind of distributions with like suitable movement conditions.
Yeah.
Okay, not only sub-Gaussian even. However, the second step, debiasing this projected gradient descent, needs this Gaussianity result. But if you want to extend that to sub-Gaussian, you need to be able to estimate its first moment and the second moment. If you have a consistent estimation, then you can still do that. Yeah. But this is the only place we use. And the undebiased procedure doesn't really heavily depend on this Gaussianity.
Other questions?
For the random initialization, you had this addition noise with the power between 5.
Yeah.
Yeah.
Is it
I'm not
less?
sure where those numbers came from. But also, I'm surprised that there's an upper bound of this power.
This one?
Yeah, that's true.
Okay, so what does it mean that alpha needs to be smaller?
Yeah.
Isn't decreasing alpha just gonna?
Yeah, that's a good point. Here, the question asks, for this random initialization, you need to have this guarantee. And this in turn requires omega n to be satisfied this for a range of alpha, right? Why do we talk about this range of alpha? So I would say specifically this alpha is an alpha of delta. So this delta, of course, gives you this kind of, you want this something close to 1, right? Or at least away from 0. And this delta, you can choose 1 over r squared, or you can choose 1 over log n, or you can choose something even, depends on the kind of this confidence level you want to choose delta. And this 5 and 13, I think corresponds to if you choose this 1 over r squared, or a kind of say 0.1 over r squared, and that will give you a alpha greater than 5. And for the other 13, I think if you take if you assume something over, let me think. If you take this delta equal to, oh, that's a good point actually. This 13, I need to remind myself. I think it's there is some additional one in addition to this. Okay, there is some kind of range you can play around with this alpha. And it's not always that you choose alpha as small as possible. It is always better because there is another condition you need to sacrifice later. Yeah, but that way is pretty modular.
It's more like a sufficient.
This is a very sufficient condition. And in practice, we found this is not like far from necessary.
Other questions?
Yes. So the reason you opted for projected gradient.
Yeah. Is there any?
Because you know how to do it, but and you can prove all these nice complexity results.
Mhm.
That's good. Is there any? I mean, sure, I can look at this as like a manifold optimization problem, but like if you talk to someone 25 years ago, they would just say, well, it's a nonlinear program.
Mhm.
I'll just run SQP augmented Lagrangian or something.
Yeah.
Is there any reason why you fell back on this? It's not a critique.
Right. The question asks, like, is there a better way, right? Like to solve this constraint optimization problem, you can treat it as a nonlinear constraint optimization.
Everything is differentiable.
Yeah, the thing is that I don't know. We didn't consider those nonlinear ones. But the reason why we chose this projected remaining gradient descent is that for our analysis, we want to characterize its first order stationary point. And this is a first order algorithm. And we found that working out its stationary points is pretty easy.
And the projection is very cheap.
Yes, exactly. The projection is 1 dimension, right? So it's very like the remaining projection is very cheap. And this one is also, yeah. So and I would point out that for remaining gradient, this is something you don't really necessarily need to use remaining gradient. You can just use the
I was just going to say, I mean, if it's a projected gradient, you don't, that's the classical gradient, you're then projecting on the.
Yes,
on the-
so if you only consider the vanilla gradient,
Yeah.
this is gonna call projected gradient descent
Yes.
without the Riemannian.
Yes.
But we're choosing to use this Riemannian gradient for following reason. First, this Riemannian gradient is essentially this vanilla gradient projected on a R-1 subdimension.
Okay.
And this is not beneficial in this case, but there are many other cases for low rank matrix recovery. There, this Riemannian subspace actually you want to project down is indeed itself a low dimensional street space. So you can utilize that structure to accelerate convergence. But in this case, I think this gradient we use Riemannian part, we use it also serves for the, it makes our analysis for the stationary point easier. Okay. Yeah.
Well, thank you very much.
Okay, thank you.